A short introduction to Clausen Integral Function. So over the past few videos, we just dealt with the Clausen function, which has a general base m of x, and the general Clausen function was defined in two cases, when m was even and m was odd. Yeah. When m was even, the Clausen function was defined as sum from k equals to 1 to infinity sine of k theta by k to the power m. Yeah. Now when m was odd, this was defined as sum from k equals to 1 to infinity of cos of k theta by k to the power m. Yes. Now, the Clausen integral function is a special case of this one where m is equals to 2. And the reason why it's named as Clausen integral function is because it has this nice and quite helpful integral representation that helps us solve a lot of problems. So that's why it's named as Clausen integral function. If we substitute m as 2, this will just be CL2 of x is equals to. Now since 2 is even, this will be a sum from k equals to 1 to infinity of sine k theta by k to the power m. Yes, and k to the power 2. Okay, so this is the definition of Clausen integral function, as you can see over here. Yes, now its integral representation is also a nice one, which you can find by taking the derivative and then summing it up. So how do we find this integral representation? Let us see. If we take the derivative of this expression with respect to x, yeah, if we take the derivative, what we get is sum from k equals to 1 to infinity, and then this will be cos k theta times k, and the k cancel out, so we have cos k theta by k. Now we can write this as the real part of e to the power I k theta. Sum from k equals to 1 to infinity, and then e to the power I k theta by k. Yes. Now we can write this as e to the power I theta to the power whole k. E to the power I theta, e to the power I theta, yes, to the power whole k. Now we know that summing this up, summing x to the power k by k, what we get is just minus ln of 1 minus x. So this is minus ln of 1 minus e to the power I theta. This is just the summation properties from logarithms. Now we need to find its real part. Yeah. First of all, let us write this as uh, in the cosine and sine notation. So this is 1 minus cos theta minus I sine theta. Yes. Now we have the separated real and imaginary parts over here. Yeah. Now, if we have to take the real part of a log of a complex number, let's say x plus iy, how we do it is real part of the log of, we know that this can be written as g to the power I theta. Yes, where g is just the modulus from x square plus y square, and theta is just the argument tan inverse y by x. Yeah, using this we can write. Yeah. Now the benefit of writing in this notation is now we get real part of the ln of g plus I times theta. We can clearly now separate the real and imaginary part. Imaginary part is the argument, the real part is the log of g. So always the real part of a complex number, real part of the log of a complex number is just the log of modulus. So also let's do that. Negative sign remains as it is, and then log of the modulus. Modulus is root under 1 minus cos theta square plus minus sin theta square. Yeah. Yes. Okay, now this is minus ln of root under 1 minus 2 cos theta plus cos square theta plus sine square theta. Yes, good. Now this is minus ln of modulus of square root of. Now cos square theta sin theta is just 1. So 1 plus 1 is 2 minus 2 cos theta. Yeah. Hmm. Now if you take 2 common, we will have 2 times 1 minus cos theta, which is 2 sine square theta by 2. Yeah. So this is now, okay, wait a second. Oh, here the input variable is x, and I should also had x over here, but that's theta. Then so let me change this to theta. I'm sorry for this issue. I'm sorry for this mistake. Should be theta. Good now, good now. Okay, good now. And this is minus ln of, this is just 2 sine theta by 2. Yes. Okay, now we have finally found out that the derivative of the CL2 function, let's see now derivative of CL2 of x will be minus ln of 2 sine x by 2. Yes, minus ln of 2 sine x by 2. Okay, now let us integrate this function. Let's integrate this function with from 0 to theta. If we integrate this from 0 to theta, if we are integrating the derivative of the CL2 function, yes, with minus integral from 0 to theta ln of 2 sine x by 2 dx. Now we can pseudo cancel the dx, and then we just have dCl2 of x. So this is just the CL2 of x going from 0 to theta. But here minus integral from 0 to theta ln of 2 sine x by 2 dx. Okay. Now CL2 of 0 is just 0 because it has it is the sum of sines. Yeah, sine of 0 is just 0. This will just be CL2 of theta, and on the other side it will be minus integral from 0 to theta of ln of 2 sine x by 2 dx. This is how this integral formula can be derived using first finding its derivative and then taking the integral of the derivative. Now we have the last thing to verify, because this is such a useful property that I think I needed to include this in the introduction itself. So yes, I'm doing it right now. Now we know that CL2 of theta is just sum from p equals to 1 to infinity of sine k theta by k square. Yes, very nice. Now, sorry. Now, if I substitute theta by pi by 2, theta by pi by 2, we will have sum going from k equals to 1 to infinity of sine of pi by 2k by k square. Okay, now, okay, so we can see that sine of pi by 2 is 1, so 1 by 1 is square. Sine of pi by 2 times 2, sine of pi is 0, so 0. Now sine of 3 pi by 2 is minus 1, so minus 1 by 3 square. And times 4 is 0. From 5 is again 1, so 1 plus 1 by 5 is square. 6 is 0, minus 1 by 7 square. Plus it goes on, it goes on, it goes on. We clearly know that this sum is just the Catalan's constant. Yes. So this is how we solve this problem. We verified this already. And yeah, we have talked about its form representation, integral representation, and its One of the cool properties is that Cl2 pi by 2 is just the Catalan's constant Z. Hmm. I think this was it. This was for today. And thank you for watching and look forward to seeing you in the upcoming videos where we will discuss about its reflection formula, its other identities, integrals, derivatives, and many more. I hope to see you there. Thanks for watching and look forward to seeing you in the upcoming videos too.